To start with, there are stickers here, and there's been stickers passed around. Please feel free to take them. The micros are mine. Please don't take them. By way of introduction, my name's Matt. Hi. I'm an engineer, software engineer for about 25 years, which makes me feel excessively old. I kind of describe myself as a full-stack engineer, which we'll talk about that in a minute, but I've been exposed to most areas of software development, all the way from low-level assembly stuff all the way to cloud-based web stuff. But a lot of my career has been spent developing on or close to hardware, which had kind of made me a bit jaded because embedded development had sort of been stagnant for a long time, and sort of watched all these wonderful developments in the rest of the software fields. But yeah, sort of saw the embedded stage just sort of plateau for a long time until MicroPython came along, and we'll talk about that today. I would describe myself as a MicroPython enthusiast. I've contributed code and documentation. I host the Melbourne MicroPython meetup, and I've talked at previous PyCons about MicroPython. So, yeah, just note on that full stack developer. When I looked up the definition of what a full stack developer is, it's like the front end and back end of a website, and I'm like, you kids. It's like, I'm not sure what you're talking about. Anyway, moving right along. Can I have some hands up? And I'm going to start with if you're human. Good. Audience participation question. I saw most people put their hands up. That's good, I suppose. Who knows what a microcontroller is? Also good, most people. How about who's written software for a microcontroller? It's quite a lot. I guess about half, more, maybe. I'm super impressed. Who knows what MicroPython is? Who went to Damien's talk earlier? Damien, you don't get to put your hand up. Good. Okay, that means I can sort of briefly go over these things. It's a Python conference. I need to know how much of the background we need to cover. So, who's seen Avengers Infinity War? Good, that's helpful. Right. What's a microcontroller? It's just a small computer, right? So microcontrollers are less about processing power when you compare them to a PC. It's more about precise, dedicated sort of tasks. They have a small amount of resources. They're limited in what they can do with RAM and flash because they have very little of it. And they often interact with the real world. So they control motors, pumps, interact with sensors, that kind of stuff. So a key defining factor is that they're low cost, from cents to dollars typically. And they've got very predictable behavior because they don't have an operating system. They tend to be just doing that one task that you tell them to do. Many systems are often comprised of lots of microcontrollers. Cars are a good example where you've got dozens or hundreds of microcontrollers in a single car. And it kind of led me on to think about the size of the market. So it's like $30 billion market, and it's expected to get to $50 billion by 2028, which was frankly a lot larger than I expected. And it seems like the average microcontroller costs about $1 because they sell 30 billion of these things a year, which if you compare it to PC sales is kind of scary. So there's a lot of these things out there. If you look around, you'll see devices in the room with plenty of them around. What's MicroPython? If you look at Reddit, it's an abomination. Quite a funny read, actually. Have a look at that. It's worth a look. But what it is really is... sorry. Okay. Tough. What is it really? It's Python 3, a re-implementation of Python 3 for microcontrollers. So a lot of effort's been put into making it work on a constrained device. Written in C. The baseline was Python 3.4, but a lot of other features have been added since then. We still claim it's Python 3.4, but there's features from all over the shop. We've added as resources allow, really. Yeah. So why should we keep updating it to newer versions of Python, new features? Especially so we can port libraries more easily from the CPython world. Yeah. We've got excellent support for the language. It really just feels like using BigPython, and yes, we call it BigPython. And we've got exceptional tests. If you went to Damien's talk, you'll know that we've got exceptional test coverage across the language, above 98%. So you can be pretty confident that the language itself is really robust and stable. If you find a bug in MicroPython, we will give you a sticker. Yeah. The standard library is a little harder. It's pretty vast, as we all know. We've got a lot of things implemented, but not everything. And a lot of the libraries are written such that they're not so conducive to work on a microcontroller. So we've got to be careful about what we put in. And it's a similar story for third-party libraries. Really tough to just pick up pandas and have that run on MicroPython. And some libraries are built right into MicroPython, and others are built in a separate repo called MicroPython lib, which we install with a tool called MIP, which is like pip. Yeah, it's kind of fun. In addition to all this stuff, we've got the machine library, which gives you access to the embedded side of things. So you can twiddle with pins, you can connect to peripherals. It's very Pythonic, so it gives you a nice, familiar sort of API if you're used to the Python world to interact with stuff that's quite low level and typically done in a much more verbose and low level way. So a quick example, just setting an LED, turning it on, using PWM, which is a technique called pulse width modulation, to flicker an LED on and off at different rates. This is much easier, and if you've been in the C world before, you'll be aware that that's a lot easier than coding it in C. Why MicroPython? And whenever I hear that term, I think of Avengers Infinity War. There's the throwback, right? Where he went, why is Gamora? That's what I hear in my head when people ask me, why do you use MicroPython, right? Why? So similar reasons to CPython. It's a readable, easy language to learn and to use. It's easy to test. It's very flexible. It's a great language, right? But the main benefit for me, at least in the embedded domain, especially when you're comparing it to C and C++, is 30%, right? 30% for me is an important number, because that's what I think the development time is reduced by using MicroPython, typically. A lot of caveats that we can put around that, but I also think we get happier customers, but that's harder to quantify. It does obviously depend on the project, but I work for a company, Planet Innovation, that uses MicroPython for some projects, and we've had a handful of projects now, and they've all come in roughly to the estimates that we said, and we've often compared them to the estimates in the C, C++ world, and 20 to 30% is pretty typical. I also expect that number to actually improve, or at least stabilize towards the higher end of that range, because MicroPython is still maturing, and the tooling is getting better, and the libraries are getting more robust. So how do we get that? It's higher level than C and C++. You're all aware of that if you're familiar with CPython. But you don't have to worry as much about memory management and undefined behavior and all that kind of stuff that you have to with C. It's hard to overstate the live REPL. So there's a way to get access to a running device and use the Python REPL on the device. So you can actually communicate to your peripherals and do a lot of work on the device itself. And that's a huge boon to development. You can really explore the development environment that way. We've got the Unix port for testing, so we can do a lot of things on x86, which is really helpful. And we've got really fast workflow, so I need to show you MP Remote, which is a tool that we use to connect to our devices, to our MicroPython devices. You can see here at this top here, there's 4 files that's on my computer at the top there. And then MP Remote mount dot actually mounts my PC file system at the dot point on the device. So it's just like my device sees the files that are on the PC. So you can see here, if I do an OS listdir, that's running on my microcontroller, and it's just like I'm seeing the files that are on my PC. It's fantastic. It's hard to explain how good this is, because it feels a bit like magic, having worked in the embedded space for some time. It means that I can develop on a PC, I can use my regular tools to do my coding, I can use Git, and when I'm ready, I can test in the Unix port, and then I can just mount it and try it on the device. It's a really low friction way to get moving. Right, so some of the other benefits we've seen, at least at the company, is that the junior developers become superpowers really quickly. And it's been really stark contrast to seeing people, seeing juniors start in the C and C++ world, where it takes a long time for that ramp up to occur. It happens really quickly with MicroPython. So that's been a surprise for me. I didn't really expect that, and it was wonderful. We've found that we're more responsive to customer requests. We can it's an overloaded term, but we're certainly a lot more agile. And customers love it. They can talk with us and work with us more. And the other thing that, for me at least, was that there's a mental change. Like, I tend to focus on the problem I'm trying to solve rather than the nitty-gritty details of how to actually get it happening and how to get it done. So for me, that's a big win. Anyway, we're like 10 minutes in, we've got background. So, right. People come up to me all the time and say, you can't do that in MicroPython, right, when performance matters. You can't do it in MicroPython if you want to run from a battery. And you can't do it in MicroPython if you want to worry about manufacturing in volume. And there's a kernel of truth in all of these, but I think it's worth digging into, right? So The most common concern is MicroPython's slow. And it's true to a degree, right? You're really comparing native to bytecode development. So just a quick refresher, with native coding, this is, if you're using C, Go, any language that compiles down to the metal, you take a code, you compile it, you're running code that the device can run directly. Right? Bytecode interpreters work a little differently. They take code, they compile it to bytecode. Bytecode gets run through the virtual machine, and then the virtual machine runs that on the device directly. And it's slower. It's slower if you're spending time in the virtual machine. There's benefits to it. Your code's more portable. There's a lot of things you can do with that, but that's the difference. The yellow bar there is just something that only occurred to me later was worth pointing out, is that all of the things that are next to that yellow bar actually occur on the device in MicroPython by default. So the compiler actually works on the device. Yeah, all the way down. And we'll talk about that a little further later because there's a way you can optimize some of that. So techniques for performance, there's a whole bunch of sophisticated methods to improve performance in MicroPython. We're not going to cover them today. Damien's talked about them before. I've talked about them before. And you need a fair bit of time to cover them. But just for completeness, hopefully these are caught on the video. You can go look these up later. I'm going to look at one performance hammer, which is just using C. All the other techniques are really sophisticated, elegant, and have their place, and they should be used. But just in terms of why you don't necessarily need to exclude MicroPython for performance, is the fact that you can use C. MicroPython shares CPython's dirty little secret in that we offload our performance to C when we need to. Not so much Fortran on embedded devices, but you know. So yeah, think about like NumPy or SciPy, right? They both got C in the guts of them. And that makes them work faster. There was an interesting white paper recently that was talking about comparing MicroPython to other languages. It was kind of weird. Like this one, for example, talks about CRC32. They actually implemented a CRC32 algorithm in Python and then tested that. We already have a CRC32 algorithm which works at the same performance of C, but they were trying to compare the language overheads. And what they conclusively showed is that bytecode interpreted languages are slower than native languages, which wasn't that surprising. The problem I have is that at the end they kind of leapt to the conclusion that MicroPython is not appropriate for embedded use if performance is a concern. And I don't think that's correct. It's kind of like saying, you know, BigPython is not appropriate for data science use because, you know, you can't, Python the language is too slow. I don't believe that. And so I think you need to take there's a bit of grain of salt to be taken here. So it is easy to extend MicroPython with C. You'll find the documentation talking about user modules. If there's one thing here we can improve, it'd be around documentation. We've got some good documentation, but could probably go a little further because it's a fairly complex topic about bridging the Python to C boundary. But the key point is that it's just C, right? Like it's fast. So relevant quotes that I have also heard, I might as well just write it in C. I think that comes back to that 30% number before. You're paying the cost of having to develop in C if you've got to do that. So my argument would be that you should spend as much time on MicroPython as you can and just optimize the bits that you need. In the projects we've had at work, there's been only minimal amounts of code that we've had to develop in C, so it's a small fraction. And the other one here is we're all human. Well, most of you put your hand up as a human, identify as a human. So, but we're always bad at guessing where to optimize. So I guess my statement would be write in MicroPython first and put it to C only when profiling shows a need. And there's a small caveat there with it almost in brackets, but there's almost no performance ceiling. Like we can drop into C and you do whatever compute you need. Yeah. You can't use MicroPython when you're running from a battery. Right? So a little bit more background. Modern microcontrollers have low power modes, and this is kind of the way that they get good battery life. A power mode means that they're sort of trading off features for power consumption. So they'll turn off the core and they'll just listen to some pins or whatever. And these can have dramatic improvements in terms of power use. And so the key thing if you're running from batteries is to drive your micro into the lowest power mode you can and keep it in there for as long as you can. That's the key thing for low power applications. So if you think about like temperature logging, it's one of the nice, easy example to think about. Temperature doesn't change frequently, so we only need to poll it every so often. So you might, read temperature every 30 seconds and you store it in a buffer. And every 10 minutes you might offload it over Wi-Fi. Okay? The key thing is to, where you're not doing stuff, drive it into those low power modes and get the benefit of running at lower power. So some quick charts, hopefully it's not too overwhelming, but that middle section there is showing that we're in a deep sleep mode and we're consuming 1.5 milliamps for this particular microcontroller. The other areas are just where the processor is running as normal and it's not normally responsive, but it's a 30 times difference in power. This is with Wi-Fi. This particular micro supports Wi-Fi as well, and you can see that the power use goes right up. That low bar there is actually the high bar from the previous slide. And so we're up in the 120 milliamps or higher if we're actually connected to Wi-Fi. Now, it's also worth noting that's with Wi-Fi just connected, not doing anything. As soon as you start transferring stuff, it cranks up again. So, a key thing to be aware of is that these low power modes have identical costs, regardless of what language you use. And the micro doesn't know that you're running MicroPython or C. It doesn't care. So the key thing is to keep in those low power modes as much as possible. There is an additional cost to using MicroPython, and that's because when the micro starts up, we have to start an interpreter. Often we have to start a file system. We have to start reading Python, compiling it, and doing something. Now, that takes about 40 or 50 milliseconds. Varies a bit port to port, but that's pretty typical. So what you need to think about is if we go back to a deep sleep mode, for example, we want to come out of our deep sleep mode and stay in that higher power mode for as little time as possible. So MicroPython adds 40 milliseconds is the way to think about it. And then if you can live with that, you can live with using MicroPython with battery-powered applications. It's also possible to mitigate that cost as well. There's a hook at the start when MicroPython starts to latch a little bit of C code if you want to. So if you can do something like wake, do a check to see if you should be woken up or if you need to, and go back to sleep, you actually mitigate that cost even. So, yeah. So, yes, there is a small cost to starting MicroPython and running in a VM, but the key thing you should be doing is keeping down in those low power modes as much as possible. And so the suggestion here is build a product in MicroPython first. You'll see a theme here. Build a product in MicroPython first, where you'll work faster and you'll get to your end goal quicker. And if you can't achieve your power budget, port it to C and C++ then. You'll have already learnt a lot. You'll have already been able to work with your customer more. You've already been able to develop the thing that you want faster. So that porting effort should be pretty small. Might be time for a drink of water. But you can't use MicroPython if you're manufacturing in volume. Again, some truth here. So MicroPython places a high demand on the resource uses of a microcontroller. It needs higher specs because it needs more flash and needs more RAM. They're the key ones. So if BOM cost, if your bill of materials cost is critical, MicroPython may not be your best solution, but it's worth having a look at how critical. So to put this in perspective, microcontroller costs tend to be in the terms of, like I said before, like high end is dollars, tens of dollars, low end is 20, 30 cents, and you sort of get a whole range in between. Now, 8 bits, yeah, I give them away. I wouldn't be surprised if we'll have stickers in a year or two with 8-bit microcontrollers stuck to them. So MicroPython's not going to run the low end. We just don't have the resources to do so. But how low can we go is kind of important to look at. Because typically when you first come into MicroPython, you'll be told that the requirements are about 200K of flash and about 32K of RAM, give or take. It's not quite the whole story. It's kind of like when we package MicroPython, it's kind of a kitchen sink approach. Because MicroPython's a dynamic language, and at runtime you need all of the features available to use them, even if you're not going to. So you have to package the whole thing. But if you know what your application needs, you can start carving it away. It's pretty easy to build your own custom firmware of MicroPython and just carve out features. So the claim here is, I guess, that kitchen sink MicroPython is around 200K of flash, and the minimal MicroPython is about 40K of flash. I'm looking at Jim because we were trying to get down there today. Yeah, he's got thumbs up, good, okay. So what can we trade off? Like features, F-strings, async, SPI, you can carve these things out at a pretty granular level. You can drop the file system, you can drop the REPL, you can drop the compiler. So you start trading off these quality of life development features to aim at a smaller micro. Okay? So I mentioned before that everything happens on the micro that's next to that yellow bar. But that red bar is actually an alternative where we can actually do compilation and freeze our code into the firmware. So it's kind of like in the C world, you would compile your application and deploy it. In MicroPython, you would compile your source code, and just like in Python, you'll get a PyC file. You'll get a similar deal. You get bytecode that you can put into your firmware, which means that you lose that ability to do it dynamically at runtime. You've got to build it into your firmware. But you can target a smaller firmware blob. Yeah. So a possible workflow you could consider is to start with like a big, monstrous microcontroller, and just don't worry about your problems. So if you're volume manufacturing, just get your application running. Use something that's got a ton of flash, a ton of RAM, and develop as quick as possible. Okay? Then shift to a micro that's got smaller resources. You can start either customizing your firmware or maybe just customizing your application so it uses less resources. And then you can do that whole nother step where you start really hacking into the firmware, making it as small as possible, and developing it so that it only supports the application that you write. And so the costs are important here. These are real examples of boards that we've got where the board to the left is the big beefy one we talked about. It's an H5 Cortex M33. I'll gloss over the details, but tons of flash, tons of RAM, about $4.60, and these numbers are all in units of 10K, which is, ST will give you these prices, but they are relatively accurate. 10K units and US dollars, so $4.60 for the big beefy one with tons of peripherals. The middle one's interesting. That's the same core. It's 250 meg Cortex M3, but they've dropped a lot of peripherals, they've dropped a lot of flash, dropped a lot of RAM, and dropped a lot of cost. And so you're suddenly looking at $1.60 for that microcontroller. But it's a pretty easy port, because if your code works on the original H5, it's usually a pretty small jump to go from the big one to the medium one. Then you've got the small one. There's a G0 that I've selected, which is at $1.20. So you save 40 whole cents, but you go into a much smaller, much lower spec micro. Now getting down to that size is more difficult, but it's not out of the realm of possibility. Right, so again, there's a germ of truth here. Like MicroPython does place high demands on microcontroller resources, but there are ways to offset some of that. And so yeah, I'd suggest, like I have in all the other ones, develop it in MicroPython first and make changes if you have to later. And that is my summary, really. Develop MicroPython, port to see if you really must, right? There's no real... The barriers here seem a lot more impressions than actual reality, in my opinion. And I guess on delivery of that thought was that I expected to find a lot more limitations developing with MicroPython. I thought it was going to be useful for a certain class of microcontrollers for certain applications. But now it's my default choice. I would need to be convinced to start an application in C and C++, and it's often the wrong choice, in my opinion. Okay, so outro, just quickly. I've already mentioned the stickers, but we're going to try and get to the PyCon Fair and Sprint Day Monday. So if you guys are interested, please stick around. And thanks for listening, and thanks to the organisers and MicroPython community, and especially to my support team who helped out with making sure all these claims were actually possible, which they more or less are. So yeah, thank you.
All right, we have time for a couple of questions, if anyone has any. Sure, I will go right here. Hi. I was wondering if you tested, and if so, what the results were around the... what kind of performance gain did you see when you froze that code and precompiled it? Did you measure that at all and see how that went?
We can cover that. It's worth talking about. So just for everyone's benefit, like frozen code, we as we mentioned briefly, we take Python code, we get bytecode out of it, that gets stored in the flash. Normally that would happen on the file system. So what we do is we avoid a lot of memory use because we don't need to invoke the compiler and we don't need to compile it. So it varies wildly, unfortunately, is the way to say it. I don't know if anyone's got any figures out there, but yeah. No, Damien's shaking his head. Damien doesn't know it, doesn't it?
Yep, I got a question. So you mentioned that one of the ways to shrink down the footprint is to custom build that firmware. Is there any tools where I can just point it to my py file and it goes, okay, you're using these things, I'm just going to build that firmware against that?
Not yet. Yeah.
We should create that.
We should, yeah.
Let's do that. That's a great idea.
We've got a sprint day Monday, right? What are you up to?
Perfect.
It would be good to do that analysis, yeah. It certainly came up during this discussion of this talk, yeah.
So it does sound like you're volunteering there, Adam. So are you showing up at the sprints on Monday and building that?
If you're in Melbourne, come along to the MicroPython meetup and we'll talk about it there. Yeah.
Right, do we have any other questions?
I'm passingly familiar with writing C extensions for CPython, the BigPython.
Yep. Thank you for using the correct term. Yeah.
Sorry, yes, I realised as I said it. I'm just wondering if you have, if you could compare the experience of writing a C extension for BigPython versus MicroPython.
It's completely different, is the short answer. I would say I found, having an embedded background, I found it easier to do the MicroPython side of things because it's kind of an obvious barrier to jump. With CPython, there was more things I had to learn about how CPython operated to create those extensions. Yeah. So if you've got an embedded background, I think you'll find it relatively straightforward. If you haven't, and probably in general, like once you get beyond the sort of the beginner range of MicroPython, the biggest ramp up that you're going to have is becoming familiar with the embedded domain, if you're not familiar with it. So yeah, I guess you'll find extensions relatively easy to do if you're sort of familiar with that. Yep.
Anyone else? Oh, cool. In that case, thank you so much for giving this talk. It's been amazing. Thank you so much.
Thank you.